Hello everybody, welcome to Unit 2, where we'll be covering the last part of Chapter 6, parts of Chapter 13, and actually parts of Chapter 21, focusing primarily on template overloading and function templates. We'll also cover the standard template library, which is a result of being able to overload functions, and we'll get into that in a little bit. And of course, our learning objectives are to be able to implement those things that we are learning. So when to overload functions, how to write function templates, and how to use structured design to solve complex problems. Function overloading in C++ is the same as it is in Java. As a refresher, it describes when you have two or more functions with the same name but different parameters. The functions differ either in the number of parameters or they have the same number of parameters but different types. So be aware though that the return type is not considered when we're looking at function overloading. We only consider the signature of the function, which is its name plus the formal parameter list. Okay. With this example, you can see that the void return, which is right here, right? The void return is not part of the signature, only the name and the number and types of parameters. So if we look at ceiling, which is part of the CMath library, you can see that it has 4 overloaded functions. Each version varies by the type of parameter that it expects. So you can see here ceiling, it can take a double, it can take a float, it can take a long double, or it can use the generic type. We'll talk about that when we talk about function templates. During compilation, compilers first look for an exact match for a function call. For example, if we have 2 overloaded functions or overloaded versions of the function fun, the first call to fun will be matched to the int version, as you can see here, function 54. Okay, it's got an int and an int. And the second call, right here, you can see we have 2 chars, will be matched to the function fun that takes in 2 chars. If there is no exact match, such as here where we only have one int version of the function, the compiler will then do implicit type conversion. Okay, so the second call here will be matched to the int version, and the arguments char 5 and 4 will be converted to their ASCII values first before invoking the function. Okay, so the result you'll see here is not what you expect. Here, when we run it, we can see that the result is 105. Okay, the first one printed out 9, the second call printed out 105, which is the addition of their ASCII values, which would be 53 and 52 respectively. If a function is overloaded with the same number of parameters of many different types and all of them have the same function body, then you may want to write one function with generic types. And we call these function templates. And this is the syntax for a function template. You have one extra line to add, which is just this part right here, template and then class type. Okay. Here, type is the data type that this function may work with. It can be either a primitive data type like an int, double, or even a class. The declaration can be a function declaration if you're writing a function template, or it can be a class declaration if you're writing a class template. And we'll explain class templates later in the course after we cover object-oriented programming. So let's take a look at an actual example. Here we have a main function that attempts to use function fun with several different data types. And here is the original int version of the function that we want to use as our base. We can define a function template with a type parameter t. This type parameter t will be used as the type of its 2 parameters and its return type. And here's a definition for this function template. It's important to note that the type parameter t can be used as a parameter type, return type, or to define local variables. And you can see in this case, we're not using it for local variables, we're just using it as for its parameter types and its return type. The return type doesn't have to be T. It can be any fixed type. Also, take a look at how we invoke the function template. You might recognize the syntax. Remember the static cast function? It's also a function template, and it can work with different destination types. Okay, so here we're using it as an int, but we could have in double, we can have in float, so on and so forth. And if you didn't remember that this wasn't a function template, don't worry about it, but it's just, you've seen this before, and so we're just trying to draw attention to that. During compilation, the compiler automatically instantiates a version of fun where each occurrence of T is replaced by the specific type in a function call. If the triangle brackets are not used in the function call, like we see here we no longer have our types, the compiler will try to infer the data type based on the types of the argument. So again, in this case, it's going to do an automatic implicit inferral instead of us telling it what types we're actually passing in. One final note on function templates is that you can have more than one generic parameter. So here you can see our template where we're declaring class T and class U, and then in our function definition we have those two variables, type T and type U, and we are using a equal comparison here to return the result. So now we have an integer and a float being passed in to A and B respectively. So this is how you can use multiple templates. Now this function has to be overloaded to be able to compare whatever two classes that you pass in. So that's going to matter depending on if you're using objects or not, but we'll get into that later when we cover operator overloading. Now that you have an understanding of how template functions work, we can discuss C++ standards template library, or the STL. Now this library defines container classes, iterator classes, and some commonly used algorithms. The container and iterator classes are class templates, and while we didn't go into these class templates directly, they're virtually identical to function templates, except that they use classes instead of functions. An example of a container would be the vector class. Okay, the container works just like the ArrayList class in Java that you might be familiar with. You have to tell it what type you're passing in, and then you can declare your identifier. Okay, very similar to how it works in Java. The algorithms, on the other hand, are defined using function templates so that they can work with different data types. C++.com has a convenient list of all the STL header files that you can include and use in your program. Okay, so you can see that they're divided up into sequence containers, container adapters, associative containers, and unordered associative containers. And we're not going to cover what all these different things means. That would be probably covered in your data structures course, but just know that there's different types of containers that you're going to see. C++.com also has an excellent list of algorithm functions broken up into several categories. First, we have non-modifying sequence operations, right? So these are things that are not going to modify the contents of the container that you're searching in. So you have for each, find, count, equal. Okay, these are all functions that you can use on the standard template library containers. You also have modifying sequence operations. So these are going to actually change the contents of what's in your container. Okay, and I'm not going to go through every single one. You can read the list, or you can go out to the link here and look at them yourself. We also have ones for partitioning and sorting your containers. Things to do binary search and merge operations on containers, as well as heap functions and min-max functions. Okay. So it's also important to note that there is a function template called swap that's been included in the header file algorithms in C++98, but it has since moved to the header file utility since C++11. Okay, so this is one that's actually used quite commonly, and it used to be in algorithms, and now it's in the utility header file. Okay, so just keep that in mind. Java provides method templates and class templates too, the so-called generics, as they are provided in the generic functions or classes. Even though we didn't cover how to write templates in our Java courses, we used class templates such as ArrayList class and the list interface. If you want to learn how to write templates in Java, such as this method template here, or this class template here, you can review the official Java tutorials on Oracle's website. Again, this isn't a course in Java, but we're just kind of pointing to some information if you want to continue your education outside of this lecture. As we move through the rest of the course, we're going to be using a lot of examples that involve strings. So I want to take this opportunity to go over some of the differences of the string class within C++. So let's go ahead and review those relevant concepts. As you're aware that we can use concatenation operators with strings in Java. We can do the same thing in C++ with some caveats. Okay. Another thing to keep in mind is that string literals, such as here you can see we have the string literal Tom and Jerry, is a C string, which is a character array terminated with a null character. Okay, it is not a string variable. A string variable is a specific thing in C++, where a string literal is a C string. Okay, and we'll talk more about this in Unit 3, but I just want to touch on some of this stuff now. When we use the plus operator for string concatenation, one operand must be a string variable. Okay, and the other operand may be a character or a string literal or another string variable. But it's absolutely critical that at least one of them is in fact a string variable, so a variable of type string. So in this example, me and you are string literals, okay, i.e. C strings. And you cannot add two C strings together in C++. Okay, this will result in a compilation error. Right. Here you can see that we are adding a C string to a string variable. Okay, and this will work just fine. However, we cannot add an integer to a string variable because T is an int, right? In Java, you could do this, all right, but we can't do this in C++. You can add a string variable to another string variable. You can add a string variable to a string literal like you see here, okay? Or you can add a string variable to a individual character. All right, those are the three things that you can do with the concatenation operator. Likewise, there are certain things that we can do with the plus equals operator, okay, or the compound addition operator. First, we can add strings, chars, and C strings, but we can also add ints. However, the int is going to be interpreted as the ASCII value of the character, right? So if we have A, it's going to be, what, 65? So in this example, right here, yep, you can see here we're adding 65 to num. In this case, it's going to be the letter A, right? And in this case, we are going to add the character whose ASCII value is 2. This is not going to add the character 2. It's going to add the ASCII value 2 to this number sequence. And so this is going to show up differently in different compilers, right? So with Visual Studio, you're going to get this little happy smiley face here. And with the GNU compiler, it's just not going to print it at all, okay? Now, using ASCII value, this expression here is going to give us an uppercase C because it's going to take the value, the integer value of this ASCII character and add 2 to it. Okay, so if we added 1, it would be B. If we add 2, it's C, and so on and so forth. Okay. And finally, remember that the addition operator doesn't accept a string and an int, and you can't assign a char to a string either. All right. So this doesn't work right here because we are attempting to assign a char to a string. We can only add a character to a number. So there's some of these really weird rules that you have to remember when you're working with C strings. So when you get compiler errors and you're trying to do some stuff like this, just remember that, oh yeah, there's some limitations of what I can and cannot do. So to close out the chapter, we're going to take one last look at some structured design concepts. And you remember in the last unit we talked about in structured design we want to kind of work in a procedural top-down design or do the stepwise refinement where we just keep tackling smaller and smaller problems, right? The critical thing is that we design first before we start writing code. And the key component of that is being able to identify subproblems, okay, within our problem. So that means that we don't necessarily want to create our implementation right away because we really need to think critically about those subproblems, okay? So this lends itself to the development of what are known as function stubs, okay? And when we use function stubs, we want to create these stubs so that way we can compile our program and run it before we add actual implementation details, right? Before we figure out how we're going to actually solve this problem, what our algorithms are going to look like inside those smaller components. We want to say, hey, I've got this high level view and I know I need to break it down into 3 main tasks. So I'm going to create function stubs for those 3 main tasks and write just enough code to make that function compile when I compile my main program. Okay, so here's an example of a function stub. We've identified through our analysis of the problem domain that we need a function that will crunch some numbers, and we know that we're going to need to return 2 integers based on the input of another integer. All right, we know we're going to have to give it a number and it's going to do some machinations and it's going to return 2 numbers to us, okay, based on other inputs, whatever that may be. So here you can see we have just enough functionality to make this be able to compile, right? We have primarily an empty body function, okay? We've got a function that's not really doing anything, right? It's just assigning a value and it's returning 0. So this is pretty much an empty function body, right? We have a fake value for each reference parameter. So B we're passing in, right, as an in parameter. So we don't need to actually do anything with B because it's an input only. But A is a reference parameter and it's expected that we're going to pass something out of it. So we want to actually assign some value to A. So that way we can test it, right? We can write code that says, okay, am I getting a value out of A? Yep. Okay, good. Okay, and then we have a fake return for every function that's not a void return type. So in this case we have an integer, so we want to return something, right? In this case we're just returning 0. It's hard-coded, so that way it always returns. Okay. The point here is that we don't care that the function works as intended. We want to be able to incorporate this into the main program and work out the implementation details later. And this allows us to, again, compile our program to make sure that the main part of the program works. And then we can go into, okay, now that I've got the main program written, how do I solve this problem? How do I solve this subproblem? And that might mean creating more subfunctions, right? And then more subfunctions and more sums. And so for each layer, you write those function stubs that's going to take to solve this problem. So in do math, we might call 3 other functions that haven't been developed yet, and we're going to want to write those 3 function stubs to solve the do math problem, right? Okay, so that's function stubs and how to use them. So this brings us to the end of lesson 2 of unit 2. I know this lesson's kind of a bit disjointed. We're talking about a couple different things, but it's really critical stuff that we understand before we start moving forward with the rest of the course. So in this lesson we talked about overloading functions and how to write function templates. Okay, those are kind of related things, related topics. And we also covered the standard template library, which consists of containers and algorithms. But you need to remember that you need to import each of those header files individually. So if you need a particular container like vector, you need to include that header file in the top of your program. Okay, the algorithm header file contains that whole list that I covered, and so you only need to import the algorithm header file. We also took a look at the string class and how to use the addition and the addition assignment operator and their limitations within strings in C++. And then finally we talked about function stubbed as part of structured design and how to use that when you are trying to solve a larger problem and break it down into smaller parts and use those function stubs. That way you can postpone how to implement those details. Okay? And we're going to talk more about structured design in the upcoming units, but it's trying to get you to think about how to solve problems in a structured way instead of just sitting down at the keyboard and just starting to hammer out code. You really need to think about your problem domain first and tackle how you're going to solve it. And function stubs go a long way to helping you solve that problem.